Alright, this is video 1 for the basic concepts of electricity. For the second half of this school year for Robotics 2, we're going to kind of take a shift and we're going to start working more on electrical engineering instead of more of robotical engineering. So for this unit, your learning goals, I want you to understand what static electricity is. I want you to understand what an electrical circuit is. I want you to understand what voltage and current are, and to understand what resistance is. So let's go ahead and get started then. Static electricity. One of the observations people made centuries ago was that certain materials that when you rub them together, they would be attracted to each other. So think about rubbing a balloon on your hair. After you've done this, your hair will be attracted to the balloon, and the balloon will actually be attracted to your hair. So here we have an example of this. And what we can think of is that for the hair, there's a force pulling it towards the balloon, and thanks to Newton's third law, there's an equal force pulling the balloon to the person's hair. Now, something else that was discovered was that two identical materials would repel each other after being rubbed by something like hair. So if I were to take two balloons and rub it on your hair and then put them next to each other, there would be a force that would repel them, push them apart. Now, what made this strange for the people at that time was that, these objects are not visibly changed because of rubbing them against something. So what early scientists thought then was that there must be an invisible fluid that's being transferred between the two objects, and they called that hypothetical fluid charge. All right, now some history here. Charles Dufay was an early scientist. I got his picture right here. And what he did was he demonstrated that there were definitely two types of charge, since there are two interactions. So what Charles Dufay thought was that, since there's this attraction interaction and this repelling interaction, that there must be two different types of charge. And in some ways, he was correct in thinking that. Then there was Benjamin Franklin. He came to the conclusion that there's only one fluid. Um, he didn't really think that there was two different charges. He thought that there was just one single charge or one single fluid. And that the two charges that Dufay saw was simply an excess or a deficiency of that fluid. what Franklin said was that if an object lost fluid, it became negatively charged, while the other object would become positively charged because it gained fluid. And there's a lot to say about this also. In many ways, Benjamin Franklin was correct about this. Um, so one of the nice things about Benjamin Franklin's theory is that it helps us keep conservation of charge in mind. The amount of fluid that one object loses is equal by the amount of fluid the other object would gain. So a lot of these early scientists thought that there was this, almost magical or mystical fluid being transferred between objects. The next important scientist was Charles Coulomb. He was a French scientist, and what Coulomb did was he used a torsion balance to measure the strength of the force of attraction or the strength of the force of repulsion. And what this did was it led to the development of a unit for electrical charge. Up until this point, scientists were just kind of, experimenting around and seeing what these forces were like. They didn't actually have a unit for anything. Now, in Coulomb's honor, we have named this charge the Coulomb. Use a capital C for that. To give you an idea for what a Coulomb is like, let's say we have two objects. One object has a charge of 1 Coulomb. The other object has a charge of negative 1 Coulomb. And let's separate them by a distance of 1 meter. So under this convention, since they're oppositely charged, they would be attracted to each other. There would be a force pulling them. And Newton's third law tells us that this force is the same on both objects, equal in strength, opposite in direction. Now, to give you an idea, the strength of this force would be 9 billion newtons. Or roughly 2 billion pounds. That's a lot of force. That'd be enough force to rip your molecules apart and turn you into a pool of atoms, basically. Now later, it was discovered that this fluid was not really a fluid. It was actually very small particles, which we call electrons. And as you might imagine, or remember from chemistry or physical science, for the model of the atom, we have the nucleus, which contains protons and neutrons at its center. And then surrounding that, we have this cloud of electrons. So when two materials are rubbed together, the electrons are transferred. It's not a fluid, it's actually particles, electrons. The material that gains electrons then will become negatively charged, while the object that loses electrons becomes positively charged. And if you remember what uh, Franklin said, this is actually the opposite of what Franklin said. So there is some discrepancies here. But what's important to realize is that scientists finally learned that it's not a fluid, it's particles. We then come to another scientist named Michael Faraday. And what Faraday did was he proved that static electricity was the same as the electricity produced by a battery or a generator. And that was a big leap forward as well. For the most part, static electricity is a nuisance. It'll cause damage to sensitive circuitry. There's not really a whole lot of use for it. Well, I mean, there's some practical uses for it. One practical use for static electricity is a Xerox machine. The thing that I use to make your tests and quizzes. That uses static electricity, and I have some diagrams for how that works here. Another use is for air filters. We can use static electricity to clean dust and particles out of the air. In the last, or another, not the last, but another example would be a Van de Graaff machine, which is fun for doing, demonstrations in the classroom. All right, that concludes video 1.